And welcome everybody. What I want to talk about the next maybe 18 minutes or so is atoms. Atoms, or on a bit of a larger scale, Legos, what I like to call Legos for scientists. So what I want to take on this little journey, showing you what my feeling is about building blocks of nature, building blocks of materials, maybe coming from these plastic bricks, which I find amazing, to basically down to these little, down to these little building blocks produced in a Danish company called Legos, down to atoms that we all use every day in every instance. But before I start this journey with you, I want to take you on a different journey and tell you about a journey that I took with my wife last fall. And we had the great opportunity to visit Brazil and visit the Amazon. And we traveled the rainforest and traveled to the nice city of Manaus. Manaus is a city of about 2 million inhabitants in the heart of the Amazon. And when we traveled there, let me tell you, it's an amazing journey because you're declining down onto Manaus, and until today, there's not a single paved road connecting Manaus, a city of 2 million people, with the outside world. So you cannot drive a truck from Rio de Janeiro to Manaus. Yet, if you go into the city center, you're finding buildings just like this one. Absolutely beautiful buildings. This building is the Opera House in Manaus. And the Opera House in Manaus is actually renowned for, number one, the operas they're playing there. But especially during the turn of the century, from the 1800s to the 1900s, Manaus was a very, very vibrant city and was known for its natural resource. And the natural resource was latex. And as a matter of fact, back then, about 120 years ago, they paved their roads with latex. Why did they do that? Because, number one, it's a natural resource and a local resource. But number two, they had this amazing place in the Opera House, and if you have the horse carriages outside, it dampens out the sound, and you can listen to the operas, right? Now, this is only part of the story I want to tell you. When you walk into the Opera House, you find a beautiful opera house inside, but what you also find is this. It's a model of the actual opera house built out of Legos. And when I got to see this opera house built out of Legos, I was reminded about basically what I do every day. As a material scientist at TEDxDavis, I'm thinking about materials, how to build materials, and how to look at atoms, the essential building blocks of our materials. And here we have it. We have a model of a fantastic device structure, as I like to call it, built out of fundamental building blocks. Now, what are the fundamental building blocks this is built out of? Well, it's basically a bunch of Legos, right? And then I was asking, what are the fundamental building blocks that material scientists or scientists in general are playing with every day? Well, you find a nice picture of our building blocks here. The interesting thing is, we only have about 115 or so of these building blocks. 115 of those are known, and this is a periodic table of the elements. You see all your building blocks, we all are made from. Now, let's take a step back and say, okay, atoms, what are atoms? Well, there's Richard Feynman, or there was Richard Feynman. Richard Feynman, later in his life, received the Nobel Prize in Physics. But back in 1959, he gave a very, very inspiring talk in front of the American Physical Society. It was almost like a TED Talk, as a matter of fact. And the talk was called, "There's Plenty of Room at the Bottom." And I believe most of you have probably heard about this. But what he was talking about during his talk was this idea, this inspiration of what good would it be to see individual atoms distinctly. Now, I believe most of you think, well, yes, of course we can see atoms. That's not a big deal. Everybody's seen an atom before, right? I think that's probably the conception of most of the people. But let's think about this for a minute. So what do we need to do to look at atoms, and what is the size of an atom? Now, if you take this Lego piece, and I measured the Lego piece in the preparation of this talk, it's about 3 centimeters in size. Now, you can get a little smaller, but that's about it. Now, if you look at the size of an atom, you're moving on the length scale, which is about this big. Right? It's really small. So this is about an angstrom, or 0.1 of a nanometer. Or in other words, it's about 300,000 times smaller than the diameter of an average human hair. So that's about the length scale a scientist talks about when we talk about atoms. Now, thinking about Feynman, what do we need to do to see these atoms? Well, obviously, the first answer to this question would be, well, why not use something like a microscope? Right? A microscope is a device with which we can see very tiny things in a lot of magnification. Now, if we were scientists and we look at pieces of Lego with a microscope, you're getting a picture like this, and it's probably not telling us very much about nature. Right? It's pretty boring experiment. Everybody knows what a piece of Lego looks like. Magnification with our optical microscope here is probably about a factor of 100. Okay? Now, if we want to look at atoms, we need something, a different microscope with a lot higher, where we can obtain a lot higher magnification. A magnification of something about 10 million or so, 20 million. And electron microscopy is a tool that can actually do that. And electron microscopy is something which has been developed in the 1930s, but now only has recently came to the capabilities that we can actually see atoms with it. And this is what I want to show you in the remainder of the talk. Now, if you ask people who has seen a single atom, and there was this really interesting guy, Isaacson, in the late 1970s, who was actually able to visualize individual uranium and platinum atoms in a material. And there's one of the first pictures he actually took back then. And only a few years later, researchers at IBM were able to visualize atoms, maybe even individual atoms, on the surface of a piece of silicon. Now, this is what IBM does, as you know. Now, let's think about looking at something in very much detail. A lot of you may remember from the news in the 1990s that NASA sent up this Hubble telescope into the sky. And the first images they received were images as the ones you see there on the left. Right? Fairly blurry images of galaxies, or I don't even know exactly what we're looking at here. But the problem was that somewhere in the production process of this Hubble telescope, they made a mistake. They made an error. And they realized this error and said, we need to correct these optics. Now, instead of getting this telescope back down out of the sky, taking a spaceship, getting it back down, repair it, and shooting it back up, it's enormous costs involved with this. So they decided to do something what they called the adaptive optics. Now, adaptive optics are basically nothing else than a piece of glasses for, in this case, the Hubble telescope. And they were able to obtain images like the one on the right, where you can suddenly see a lot more detail. Now, can we do the same thing with an electron microscope in the spirit of Feynman to make the electron microscope better to produce more detailed images? And I wouldn't be here if the answer would be no. So, as a matter of fact, I probably would have never graduated if the answer didn't. Now, on the left-hand side, you see a picture of a piece of silicon. Silicon crystal. The crystal is a very highly ordered arrangement of atoms. And if you turn the crystal in a certain direction, you will find atoms, or numbers of atoms, which are separated by each other by a very small distance. It's about 0.78 angstroms. Incredibly small distance. And with electron microscopy and these adaptive optics, or a pair of glasses for your electron microscope, researchers in 2004 were finally able to visualize this, to separate atoms that are that close together. And only a couple of years ago, researchers at Berkeley were able to push this what we call the resolution limit down to 47 picometers, or 0.47 of an angstrom, or 0.047 of a nanometer. Or about 30 millionth of the diameter of human hair. It's incredibly advanced. Now, also, you all know that last year, the Nobel Prize for Physics was awarded for the discovery of graphene, a new material. Graphene is a single layer of carbon atoms which are arranged in a very specific arrangement, as you see on the left-hand side of the slide. Now, this is a fantastic material since it has fantastic properties. If you were able to build a hammer out of a single layer of carbon atoms that are arranged like it's shown here, you would be able, and tie this hammer between two trees, you would be able to place a cat in this hammer and it would be supported. Imagine a single layer of single atoms, right? Incredible. Now, it's only been last year that researchers were able, for the first time in history, take a picture of a single layer of graphene. And here's a picture of a single layer of graphene. You can see that the arrangement of the white dots in the picture is very similar to or is actually the same as the arrangement of the carbon atoms in graphene. And in this particular case, there's a little hole in the little hammer of graphene. And they were able to videotape how the atoms are moving around this hole, basically because it was at a certain higher temperature. So now we are able to see these individual atoms, to see individual graphene, individual carbon atoms. Here's a further advance just published last year, where people were finally able to basically take a piece of graphene, but instead of taking only carbon atoms, they put boron and nitrogen atoms in this layer. Now, for most of you, probably for me as well, this is pretty boring. What's so interesting about boron and nitrogen as a layer of graphene? Well, what's interesting about this study is that we're not only able to visualize where the atoms are, but we're also able to say this one spot is a boron atom, this other spot is a nitrogen atom, and by the way, we also have carbon atoms there, and we can also put oxygen atoms in there. So now we are not only able to tell you where the atoms are, but we are also able to tell you what kind of atom it is. And this is something which really goes way beyond what Feynman had asked for many, many years ago. You can not only see distinct atoms, we can also tell you what kind of atom it is. Now, this is a lot of science. Let's go to something which is a bit more technological, or what's driving technology. So what you see here on this slide is, on the left-hand side, is a picture of the first field effect transistor. Or in other words, it's just a switch for current. What these researchers have done here, they're putting some current here from the right-hand side, putting it through this device to the left-hand side. And they can switch this current by hooking up a battery to the base plate of this device. Now, why is this interesting? Every one of you probably has a cell phone on you right now, or a computer. I've seen people with digital cameras and iPads. Now, each single one of these devices has a few million, if not even a few billion, of these devices built in. Now, this first device in the 1940s had a size of a few millimeters. Now, imagine how large your cell phone must be. You put a few million devices in there, each single one of them having a size of a millimeter. You couldn't carry your cell phone like that. So this is an incredible success story of materials research and semiconductor industry to build these devices. Now, when we do electron microscopy with these devices, right, you see here we put a silicon chip, a silicon wafer onto an optical microscope, and we magnify this, and we see that these transistors, these electronic switches, now have sizes about the length of 45 nanometers. Okay, so this is sort of the length scale we're talking about. So if you bought a computer in the last couple of years, you will have transistors in your computer which look like this one here on the right-hand side. The colors in the picture tell you that there are different atoms, different building blocks in there, and tells you how these different building blocks are arranged in your transistor. Now, what's a lot more interesting is actually, from a scientific standpoint, is not this 45 nanometer length, but the much more characteristic length scale, the characteristic distances in your devices, is the thickness of these layers you see here in the upper right corner in that image. What you're looking at here is an atomic resolution image of a transistor, of an electrical switch extracted from a laptop computer. And the thickness of these films you see there in the current technology is about the length of, I think, 9 atoms at the moment. If you buy a computer from IBM, the length of the thickness of these films corresponds to 9 atoms put right next to each other. The next devices in the next couple of years, or maybe 5 years, will probably be down to 5 atoms. So this is an incredible technology where eventually our understanding of electrical engineering will break down because we are down to the single building blocks of our materials. Now, we can go in with microscopy and find single atoms in these devices. We found that in these very thin films, there are single atoms in there which actually do not belong there. So we took pictures of it and we found that these atoms actually cause the computer chip to fail. So if your laptop computer or your cell phone gets really hot and breaks down eventually, it's these atoms which cause that. And we can use electron microscopy to take better pictures than just this one. What I actually wanted to show you is a video that we can see these atoms. We can see these atoms in 3 dimensions. We can now take pictures of single atoms in 3 dimensions, take videos, and you would actually see how this computer chip turns around. You can see it, look at the atoms from all different sides. Now, unfortunately, this video is not going to play. And I already spoiled you the surprise that you can actually see these atoms. So I'm going to move over to the next slide and say, now we can look at atoms. We know where the atoms are. We can look at atoms in 3D. We can see single atoms. Where do we go from here? Is there still something to do? And again, I wouldn't be here if I thought there's nothing to do. So there's a lot to do. Now, what I think where the future will be, going back to the Lego pieces, taking a device structure and disassemble it, taking a computer chip and take it apart atom by atom, and think about what would be a better device structure, what would be a better design for the next computer chip, and put it back together atom by atom, and maybe build a better computer. Right? But of course, this is not restricted to computers only. Talking about computers is just convenient for me because I work in that field. But there are a lot of examples out there in our daily life. So I showed you that we are able to see these individual atoms, right? We can distinguish the atoms from each other. We can know what kind of atoms these are. We can take these tiny little electronic devices we love so much and look at them in the most incredible detail we can think about. Now, maybe we can look at these atoms and with the technologies that are emerging right now, something what we call in situ, in vivo, in vitro technologies, we can actually go in and take one of these atoms and move it to a different place inside your device structure. Or take this particular atom which causes all these problems, take it out and replace it with another atom. And maybe we can do this in 3 dimensions. We can look at it in 3 dimensions and put these atoms into the next generation solar cells so that our solar cells are no longer 20% efficient, but maybe become 50% efficient and we can solve our energy problems with them. Another way is, I talked about the emerging technologies that we can contact individual atoms now electrically, put a current, put an optical device on it. You can move the atoms around. If you can move the atoms around and manipulate our materials on the atomic length scale, maybe what we can do, we can tackle viruses. This upper right corner is a picture of the influenza virus We can take these viruses, take atoms out, put different atoms in, and change the effect these viruses have on the human body. There is DNA. Maybe we can, this is a sore topic, of course, in public, to manipulate DNA somehow. But if we can change DNA on a molecular level, and maybe take DNA, modified DNA, or a modified virus or bacterium, and put it into something like on the upper side there, maybe a carbon nanotube. Put it in there, and then we have a carbon nanotube is a very small container, basically. That's all what it is. Put these viruses, put these atoms in there, and deliver it to a specific area in your body. And maybe the bacteria we can design can destroy cancer cells. We may be able to very specifically, very locally cure diseases, right? Another example could be if we can modify crop growth in plants on the atomic length scale, we can engineer it from the bottom up and then maybe cure some of these problems we have in the world with hunger and so forth. So this is really looking maybe 20, 30 years in the future. So with this I want to finish up and maybe give my vision of science, looking at, or inspire especially the young researchers, thinking about what kind of experiments can we carry out. I would like to claim that the most boring experiment we can carry out in our laboratory is the predictable experience, or the predictable experiment. If your funding agencies ask you, can you really do this experiment? And you can say, yes, it already defines something like a boring experiment. Because I think it's the seemingly impossible experiment which will really drive forward technology and scientific gain. And the last statement to make, I think, sort of Feynman's notion, I think there still is a lot more room at the bottom. Thank you very much.